Okay, so last time we got our OpenGL triangle drawing working. Right now, the next step is to create a simple API, or not simple API, but just a simple set of functions which are APIs for our game to draw something, right? And so the basic thing we will need in our game, which is our Pong game, will be needing a rectangle. We should be able to draw rectangles, right? So the requirement that we should be able to draw some form of rectangle, right, like this, or you know, some form of rectangle. Currently we can draw triangle, but to draw a triangle we need this data, and then we need to set these buffers, vertex attributes, and then we call this gl draw arrays to just get something on working. And every time we want to draw something, if we do this kind of thing, you go crazy. Right? So let's say how we can abstract out something and create a sum API which we can use very easy, right? So the first thing is to abstract this data out, right? So currently we know that this is position, this is colors. So let's just create functions or just data type, right, which will call it vertex. So this would be a struct, and this would be what a vertex can store, right? So basically we know that in one vertex we are storing position and color in second. So these are like one vertex of data. So vertex can store position, right, which would be, so the position is, currently we are only dealing with 2D vectors, 2D 2D drawing. So for 2D vector we'll need a data type. And so what we can do is, above here we can create a vector 2, which would be just array of float 32, right? So vector 2 would be an array of float 32, which would be a two-dimensional array. And we can also say it distinct, so it would be distinct from any other two float array, right? So basically this is a type, and what we are saying is, if something else is of type this, this and these are not the same, because we have written here distinct. So if we want to convert this to this, we have to actually cast it explicitly, like we need to tell our let me, we need to tell compiler to explicitly cast this from TFT to vector 2, right? So that's what distinct. So now position would be vector 2, and then we'll be storing a UV coordinate, right? So we'll be storing UV coordinate, which would be also vector 2. So this UV coordinate will help us do some texture work, or if you want to do some sort of drawing in the shader itself. uh, Mainly we use this UV for texture mapping. So later on in our render we have some image, right? So we might have some image, and we want to draw this image onto this rectangle. So we need to map these coordinates of image to the coordinates of a rectangle, and that's where the UV comes in, right? So we'll also do that. And then we'll do vertex color. Color is a four float array. So we'll just do this, right? And so now we have vector 2 and color. So we'll just define this as color. Right. So now we have basically a data which you can say, oh, this is one vertex, and now we can have some form of API, so we can push this vertex onto our data structure, right? So basically this is our data structure, which will be like simple array, and we'll just populate this array whatever data we want, and then we can just pass our data at once to GPU to draw this data, and then we can say, oh, let's draw this data, right? We'll also need a render state struct which would store our current state of our renderer, right? So what I mean by that is that we have this vertex buffer object, vertex array object, which we need to store, and also this data, right, which you need to store in somewhere, right? Also we also have a shader, right? So we have this shader ID which you need to store. So let's do that. And for render state, we have VBO, which is U32. Yes, so we need to store VBO, VAO, and also we need to store our basic shader, which is U32. We need to store our vertices, which would be a slice of vertex, right? So this will allocate this vertices, uh, we'll allocate these vertices whenever we want to. Thanks for the follow, Mercy. Yeah, so now we'll have this vertices array which will allocate each individual frame, and then we can populate. So now let's align this, right? So now we have a render state, and let's create. So what we'll do is, when a program starts, right, so here we initialize our OpenGL, and if we have done our initialize OpenGL, I don't think that matters that much. Let's just do render state, and let's just do render state here. So now we have this render state variable, and what we'll do is, when we load this shader, we'll load it into basic shader, right? And then we load that. Okay, so next thing would be for VAO and VBO, which currently will be abstracting this, will be moving, extracting, not abstracting, will be extracting this out into something else. But what we gonna do is that we'll draw the triangle, we'll draw the same triangle, but with a little bit different, uh, what we can say, a little bit of with our apps, our extracted API, right? So whatever API we have created. So first of all, we have this vertices data, and we need a way to push this vertex data into the vertices, right? So we'll just create a function called push vertex, and this would take in our render state. Sorry. So this would take in our render state, and also the vertex that we need to push, right? And then that's it. So now what we can do is we can use this vertices and then put into something. But when we push a vertex, we also need to keep track of like where we want to push our text to, right? Because we have this array, right? And so at the start, when we push, we want to push it here, and then when we want to increment our index, right? So for that, we'll have vertex count, which would be u32, right? Yes. And so when we do push vertex, so when we do push vertex, we just take in our render state dot vertices and render state dot vertex count. Oh, yes. So for push vertex, we'll not take this data type directly. What we'll do is we'll say that you need to pass in position, right, which is vector 2. You need to pass uv, which is vector 2. So we can write in odin like this uv, and so these both are of same data type, so we can write it together. And then you have to pass in color. So basically we take each of this information differently, because we don't want our API to be bound by some kind of data type where we tell our user means some other function, not some other user. Like we are only doing this, but I don't want somebody using push vertex to know about this data structure. Like this data structure will be used internally by our renderer, and there is, yeah, so we don't need to take this vertex. So what user will have to do if we do vertex is that he has to first create this vertex with this data, and then we pass it. But that would be a little bit more complexity on the side of the user who is using this function. What we want is just pass in straight data, and then we'll handle all these things ourselves. So we can do vertices. So this would be our like first vertex, right? And so in the first vertex we can just do position is equal to position, and then we just need to duplicate this 2 times, and then we can do uv. So we'll just copy our uv, same thing for color, and at the end of this, what we need to do is we need to increment our vertex count by 1. Right? So this is like simple, very simple uh, thing where we just pushing in our data, and then we are just setting the data into our buffer, right? So we have this vertex buffer, and we are setting our data into that. Now because we have this push vertex, we can use the same function for push rect, right, where we basically where we'll take in render state, which is necessary for all the functions we have. And now we'll be taking information regarding rectangle, right? So how we want to create a rectangle. So basically what we want to do for rectangle is, for drawing rectangle we only need two information. Like one is this point, which we can call the position, and one would be the size of the rectangle, right? So basically position and size would be how much width it is and how much height there is, right? So we can just take those two things. So we can say, or we can just say this point is minimum point of the triangle, because it would be the minimum, not necessarily. Yeah, let's just do position and size, and later on we'll add something called offset. What this particular thing will do is that if you want to pass a position which is center of the rectangle, then we can set our offset to 0.5, and then our position would be transformed from here to here. We'll see that once you see it in the action, you'll understand what I'm talking about. But currently, we'll just do very simple case where we are just passing for rectangle. We'll pass position and size of the rectangle, and then color. And now we'll write some same thing where we put our data into this thing. So from position and size, we can create like we'll need to create like four vertex, right? For rectangle, we have this information, and using this information we need to create four vertices. Let's call them A, B, C, D, right? So A vertex is very simple, so let's create a vertex A. Yeah, let's just do vertex A. Do we want to do this way? No. Let's do A. So this would be the position. So this would be the position because position is this one. And now B point would be A plus size dot x, right? So yes, would this work? Would this compile? Variable declaration must be identifier. Yeah, that's the problem. Okay, that's yeah. So we can do that. We need to convert this into vector and like this, and then C would be A plus vec2 of 0 comma size dot y, right, like this, and then D would be A plus size. So this is how we'll calculate four position, and then we need to calculate also the UV coordinates. So we'll say AUV. So AUV would be very simple for right now. It would be 0 comma 0, because we are not using texture, so we'll just set this as 0 comma 0. This is 1 comma 0. This would be 1 comma 1. This would be 0 comma 1, like 0. So B, C, E. So B would be this, 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 and this. And color would be same for each vertex, because we want a rectangle to be all white or all black or all orange, right? We don't want this transition. And if you want the transition of the color or some form of gradient, we will be able to do it in future. So let's call our vertex function where it takes render state, and then it takes in position, which is A, it takes in UV, which is UV, and then it takes in color, which is which they have. And we'll call this two times, and the order, now remember the order, right? So basically to draw a chord, so if we want to draw a chord, we have to draw it in the triangle form, right? So let me change the color here. So if I have a chord which is A, B, C, D, how I want it to draw in actual OpenGL thing is I want to split this into two triangles, right? So I will draw this ABC triangle first, and then so basically I'll draw ABC triangle, and then I will call CBD triangle, right, like this. So I have to call this push vertex function 3 times, one for one triangle. So here we can just put a small note for future. So draw a b c triangle. So here we are not drawing ABC triangle, so we can just say data for ABC triangle, and then here we have data for CBD triangle, right? So we have to set it up this way. We have to set up our data this way. So then we can when we draw arrays, we are drawing triangles in a continuous way. So we are drawing this triangle first and then this triangle, right? If we don't set up our data this way, OpenGL would not understand what kind of data this is, and it would draw triangles which are not in order, right? So we'll do A, B, C, and then B, C, and then here we want to pass C, B, D, C, D, D, like this. And these are like push, right? Where we push, the function suggests that we are pushing some form of data, which is rect data, into our buffer. And yes, now, yeah, so let's also define how we gonna use this code, right? How we'll be able to use this code. And so first of all, we need to remove this declaration thing here, but that would be problem. So we'll also need to do okay this, yeah. So render basic shader undeclared name render, yeah. So it's not render, it's a render state. So render state, like this, and then so how we gonna use is something like this, right? So this is our API. So let me write a use case first so we understand how we are gonna do this. So we'll have something called immediate mode, right? So we set our vertex count to 0 here, and then we'll have immediate flush. What this flush function will do is basically this will, whatever information we have set in between these two functions, right? Whatever data we have set, whatever we want to draw, we'll set up here. So basically we'll call here push rect function, right, multiple times. So here we are setting our data to be 0, and then we are setting up whatever data we need, and then we'll call this immediate flush function, where whatever data we have, we'll use that data and draw stuff onto the screen, right? And so we know to draw stuff onto the screen we need all these things, right? So this thing we can only call one time and we can get away with stuff. Yeah, so there are a couple of things which you only need one time, which is this, right? So let's separate that thing, and now we have here this particular way we want to draw stuff, right? It's very simple and very straightforward how we can draw stuff onto the screen. And so size we don't care right now, so we don't care about like size of a thing, yeah. So this whole thing we should be only be called one time, right? Because we are setting up our what kind of data we have and all these things. So we can just do it here, right? Okay, so we don't need these variables because we'll use our render state variables here. So we are generating vertex buffer, we are generating vertex array, and then we are binding that, we are binding view, and then when we call our buffer data, what we were doing earlier, where we were passing actual data which we want to set, but currently, as we know, we don't have any data at the start of a game, right? So what we can just do is we can just pass in nil. I think we should compile. So yeah, in bind buffer we need to set our state, and then here also we need to set up a state. So currently we have error regarding these functions, so let's comment those out. And size, so size, I think we can just do 0. Vertex buffer, okay, let's look into documentation for this, so we are sure we are not making any error here. So let's do buffer data and let's go to GL4. Okay, so it's a pointer size, specify size in bytes of the buffer object, new data, so data, yeah. So here we can pass in null if no data is copied, and so we can also set this as 0. And now we can't here, we should not pass in static draw. What we should pass here is a stream draw, right? And the reason for doing stream draw is now we have this buffer which we are using to streaming data from CPU, right? So we have a buffer onto the CPU which is this vertices, and whenever we want to do something, whenever we want to draw some information or draw some shape, we are setting those data into our CPU buffer, and then we have this streaming buffer onto GPU which we are creating using this GL gen buffers, which is vertex buffer. So it is something we are using for streaming in data from our CPU, and that it is gonna used for draw. So that's what we are specifying here, that this buffer is will stream in data, and then this data is gonna be using for drawing stuff onto the screen. Then we are setting stuff up here based on what our buffer is, right? Like how, so we, if you know what we are doing here is we are specifying whatever data we are sending, which is plain old data, how shader will understand this data. So we have in our shader, we have this layout position, layout color, and these are all how you can read this plain old plain data into that particular format that we are defining here. So currently we were defining like in floats. Now we can just do here size of vertex, because now we have defined that, oh, this is my size of the vertex. I can use the same size here. Also, if you notice something, we have one more attribute in our vertex. Yeah, so now we have 3 attributes. So we have, so in our shader we only have 2 attributes, which is position and color, but in actual our vertex we have position, UV, and color. So now we need to also use that UV layout. So what I'm going to do is copy paste this. I'm going to make it 1 2, and this would be like UV coordinates, right? And same in fragment shader will take in vec2, which will be UV. We won't be using UV for anything, but we just need to set it up so we can use it later when we want to draw textures. So we have this UV, and then we have to pass this with this, and we also need to create out variable for FUV. So now we are setting whatever incoming UV into FUV, which will be passed into fragment shader, and then it can be used for some things. And now we need to define how these attributes we need to define how shader can read this attribute from our data, right? So that's what we do it here. So we define that this first position is the size of vertex and it starts from 0. It is a two float number, right? So for second thing also, it's a, so we can copy this line, and this would be 1, this would be 2, this would be 2, this would be 1. So now the like second attribute is also two float number, which is also size of number, and this has an offset of size of vector, right? So basically this is two float number, so we need to have this size to vector offset, because when you access this UV, we need to offset it by position 2, right? Our position data is on top, which is two float number. We need to ignore those two number, and then we need to come to here. So this is how we define offset. So this is offset of two float from the top of the vertex, like top of the data. Then we have this color data, and for color data, the offset is, for color data the offset is 2 size of vector. So when you take offset of two vectors, you then come back to the color. And so this is how we are defining our vertex attribute. We are loading our shader, and yes, so this would, so our game code now would come here into here, and here we'll draw our stuff. We'll get rid of these two calls also. Yeah, so these two calls will now be used, not, they won't be used there. Where they will used is in our immediate so in our immediate flush, which takes in render state like this. So we'll be using program which is a basic shader, right? So we'll use this program to draw something, or you know what we can do better is that let's also have current shader, right? So we define our current shader when we want to draw something, and then we use that current shader to draw something. So rather than this, we'll just use our current shader, and then inside the draw arrays, here we'll have to define how many vertex we are drawing, and we know that easily because we are keeping track of that vertex count, and so we'll just keep that here, right? So this is nice. We need to bind couple of things. So we need to bind a buffer, we need to bind our buffer and vertex array before drawing. So let's copy paste those things here, so we can bind this thing, and now we can draw stuff. And after we draw, we want our render vertex count to be set up as 0 again, because now we have drawn all of our geometry which was in our data. Now we have to set this up, and also we have not set up, we have not send our data from CPU to GPU to draw, right? So before drawing, we need to set whatever data we have in CPU, and we need to send it to GPU buffer which we have created. And for that, we have function called subbuffer data. I guess it's something like that. Subbuffer data, GL sub No. Buffers update. Oh, it's a GL buffer update. Yes. So updates a subset of a buffer object's data store. So we'll be using this. So buffer subdata. So using this function, we can set a data from CPU to GPU inside whatever buffer we have found. So we have this array buffer found. So we'll use that array buffer and then specify the name of the buffer object, GL name. Okay, we are using GL sub buffer data, so we don't take them. We need offset, so we don't have any offset. We want to write our buffer from the 0 place, so we are not setting any offset from the start of our buffer. We want to write it from the first buffer. So this is our GPU buffer, so we want to write it from the like 0th place, like we don't want to set any offset where we want to write, right? Then we have to define size. So size of the buffer, I think this is size in bytes, so we can specify the size in the bytes of the data. So the size of bytes would be how many vertex, the size of the vertex, and then multiply by vertex count, right? So how many vertex we have and what is the size of one vertex, and that would be our size of the vertex, and then specify a pointer to new data that will be copied into the data store. So this would be our vertices, right? And then if we compile, we'll get error cannot assign value of type u32 to int in the procedure argument. Okay, so we can set this vertex count to be int. I guess I32 would work. No, so let's define them as int, so we don't have to cast. And then draw arrays of int I32. So we need to cast this to I32 like this, and this would be render state. Now we have a problem where, so we need, so because this is a slice in Odin, and what slice is in Odin is very simple. So slice is basically a pointer. Let's say this is a slice. So slice has a pointer to data where the data starts, and then pointer to data where it ends, and it also holds the length of the data. Like that's it, that's a slice. So uh, open C++, so this is because of the C++ API, it does not understand what a slice is. We need to pass in explicitly this pointer from the data start, and we are also passing in the size of the thing. You know what, we can also do length of, yeah, okay, no problem. So Odin has a function. So what we can do is we can pass in the reference of the first element of our splice like this, and it would go away. You can also do this. Also Odin has a function called row data which does this by default, and I like using this function because sometimes there are some little bit of complicated thing you want to do to convert your slice into raw pointer. This does that for you. So yeah, I guess I like that. Okay, so now we have this thing done, and we'll also will create a begin function. And why we are doing this is to simply call this function, right? So because we want a block thing for our API, the sole reason is to do something like this is because if I want to draw something with different shader, right? I can write these blocks and I can do multiple drawings, right, with multiple draw calls and with multiple shaders, because here I have to specify that my current shader is this basic shader, right? And then I set this shader, and whenever I do flush, I use this shader to draw my things. If I have multiple shaders, I can write another block, right? And then I can just do any, let's say I have some complex shaders or some light shader, right? Whatever shaders. So I can have these multiple blocks for multiple shaders and in future multiple textures, right? This is not the ideal way to do something, but this is the simplest way to do something, to draw, right? And later on we'll extract the patterns out of this thing also if you want to do something, right? But currently this is the simplest and straightforward way to extract out a drawing code into some small functions where we can do stuff, right? Okay, so now let's get our drawing rectangle working. So for push rect, we want to draw a rectangle at 0 comma 0. So I'm gonna pass it 0 comma 0. Okay, the push rectangle always takes in render state, and it takes in pointer of the render state, then it takes in position, then it takes in the size of the rectangle. So let's define size of our rectangle to be 0.5 0.5. I think 0.5 would cover the whole screen. No, no, it would cover the half of the screen. And then it also takes in the color. And let's do one more thing, because we have this color thing. Let's define some global variable for color. Right, so we can do is we can define white color variable, which would be 1 comma 1 comma 1 comma 1, and let's define some colors. So we'll also be defining black color, and then red color, and then green color, and then blue color. So let's rename this to black, red, green, blue, this. And now we can just pass white, and hopefully, so immediate begin also takes in this render state, and this also takes in render state. Parameter render state of type is missing in procedural call. Oh, did we? Yeah, so we forgot to pass in this. Okay, and here we need to pass this, and it compiles. Let's hope we have made a lot of changes, and if it runs on the first thing, that means I'm genius. Just kidding. Okay, so yeah, definitely does not work. And so there is error in 67. Oh my god. Okay, so what we forgot to do is we never initialize this vertices data. Like we have never assigned any data to this particular thing. So where what we are gonna do is this code runs in loop. right? And it keeps running, right? It just keeps running. And because we are manually managing our memory, Odin has a cool little concept of allocators, right? Which makes managing memory so easy, so easy that you haven't thought of a way to manage memory. And people who program in C also use this same concept of allocators, but they have to implement their own allocators. Here we don't have to implement our own, we can just use what language provides us. And there are couple of different strategies how you can implement allocator. There are different kind of allocator, different kind of arenas. There are not different kind of arena, different kind of allocator. There are simple allocators like arena allocator, then there are buddy allocator, then there are general purpose allocator, then there is temporal, right? There are different conceptual way you can create this allocator to help you memory manage, and it's very simple, right? What we are currently gonna use is what Odin gives us. This Odin gives us by default two allocators, right? One is allocator, which is general purpose allocator, which behind the scene use malloc and stuff, whatever simple procedure there are. And there is one more which is temporary allocator, which is also using the same thing, but this temporary allocator, you can, this is general purpose allocator which you want. If you allocate some data using this allocator, you want this data to persist throughout the application, and you should be able to free whenever you want. Temporary allocator, what we do is when we need some data to do some calculation, but we don't need this data to be persist throughout the application. It should be only persist through one frame, right? So we have in our game, we have a concept of one frame. Our data should only persist through this one frame, and this vertices data is a memory like that, right? At the start of our frame, we want our memory to be zeroed out, right? There should be nothing in it. Then we write bunch of data into this memory. We are using this memory to draw something, but now when the second frame starts, I want this data gone, right? I want to clear this data, and I start want to filling this data again, right? And so whatever we use in this temporary allocator, it doesn't allocate every time. What it does, it just frees, it just clears out our memory, and then we reuse this memory again. We clear out this memory, we use it, right? So uh, before each frame starts running, right? Before each frame starts running, I guess the frame actually start running here. So what we'll do is basically we'll call free all, and then we'll pass in this temp allocator. I guess free all is the thing, context, yeah. So this context variable is passed through each and every procedure in Odin implicitly, right? This is the variable which passed inside this argument, but you don't know, like it just passed in implicitly. If you don't want this to be passed in implicitly, either you can type the C thing, or you can say context less like this, and it won't pass in this context. But it's more on how the Odin works, right? uh, yeah. So now we are freeing whatever we have allocated with this temp allocator at once, right? We are not setting our free thing like multiple times throughout like our one frame. We, whenever we start our frame, we want to free our allocator. We want to free each and every memory, not free, my bad. We are not just freeing, we are clearing whatever memory we have allocated, right? We are just clearing the memory. We will allocate it at the start of our program, which Odin does by default, and then we are just clearing the memory, and then we reuse it again throughout the frame, and then we clear it again. So basically we are using the same block of memory uh, throughout the whole process of our game. And then after doing that, we cleared our memory in the temp allocator. And before this thing, what I want to do is I want to make, I guess we use make, right? Yeah, I guess I need to check into the documentation because I'm also new to the syntax of the Odin. So let's go to overview and let's do slice. uh, do we have how we can make slice? Yes, so we can make slice like this. Yeah. So basically we do make and we pass in what kind of data we want to allocate. So we need to allocate slice of vertex. We also need to define the size, the total size of how much size we want. So currently what we'll do is we'll just define some constant here, and the constant would be like, let's do max vertex. So let's do max vertex and we'll define, okay, let's do one more thing. So let's define max chord. So max chord would be how many rectangles we can draw at once in one draw call, would be something like that. So let's define we can draw 512 rectangles in one draw call, right? So uh, in one draw call means one GL draw arrays, and so for that we need max chord. And remember, each vertex needs, each chord needs 6 vertex. So we need to multiply this by 6, and that's how many vertex we need, right? So basically one chord has 6 vertex, 1 2 3, because it uses two triangles and two triangles need 3 points. So basically we need, in one chord we need 6 vertex, so we are multiplying it by that. And we can also uh, make this number little bit more. I think 512 is fine. We can do 256. And remember, this is not how many rectangles you can draw on the screen in total, and these are not total, these are like in one draw call. In one draw call you can how many draw, and you can, and in one you can do multiple draw calls, right? There is no limit on how many draw calls you can draw, right? So but in one draw call we can use this method, which is fine, right? We are just designing something, and this is fine for our game. As you make your game complex, you see these patterns and then you start to understand, oh, you can make this also dynamic, right? So now you don't have any limit, you don't have any hard limit. But I have realized in developing something like this that creating some hard limit around things like this is actually very important. Not important, but it actually helps, because when you have some form of hard limit, you understand, oh, I'm never going above this limit in my whole throughout my whole game, right? So you understand this. You can do dynamic, but whenever you go above this limit, you understand, oh, this is a part of the code where I need some form of larger limit to my code than this. And then you can start to check out for the patterns. Oh, where am I doing this, where am I doing this? And then you can create some routines or some form of data structure where you get rid of that hard limit. But if you don't need that thing, that's fine, right? So we'll do 256 and max chord, and then when we allocate this memory, here we can just say max vertex. I think this is in size. No, okay, so this is just like integer, so this is fine. And my bad. So I have to do vertices, and now you know that so how this allocates is from the general purpose allocator. We don't need that. What we need that is we want to allocate using temporary allocator, so it gets freed at start of our frame. And so now if I run, okay, so we are getting error is something called, so we are getting error in GL invalid value at 102. I don't know, so it's an error for GL buffer sub data. So we are doing something wrong. I guess we are doing something wrong. So we have this push rect, right? So in the push rect, so it gives that we are sending 192 bytes. Is it now 192? So we have 6 vertex, and let's print out size of vertex. Oh, okay. So we need to set couple of things here. So whenever we push a vertex, as we told it, we'll be asserting here that our render state dot vertex count should be less than max vertex, right? So here we'll assert something. So whenever we do something crazy, we get this assertion error at runtime, and we know why something is not working. And so we'll keep checking whenever we push vertex. We'll check if vertex count is less than max vertex. We are not going above that, going above our limits. And same thing we'll do with immediate flush. We'll only do flush if our render state dot vertex count is greater than 0, right? Right. So we'll check this also. If we don't have any vertex draw, we should not be calling. Okay. So we are still having an issue. So we have 32 and 32. 32 is the size of our vertex multiplied by 6 is 192, which is fine. Hello, coffee guy. How are you? Coffee guy 1321. So buffer data, GL, not that one, GL buffer data. Yeah, so specify the size in bytes, the buffer object. Okay. I understand. So yeah, I am so dumb. I am actually dumb. So this buffer data, we have to define that how much size you need to allocate inside GPU by defining the size here, right? And that's why we have this max vertex. So this much size we need, this much size we need. How much size we need? So we need maximum vertex data and size of one vertex. And I guess let's go. We got a rectangle working. So I can get rid of this debug code. Everything is fine. And now we have this point. We have this rectangle. But there is one problem. The problem is there is no problem. But if you remember how we wanted to draw this triangle was like this. What we defined for the position was this was the point, and then we go down and like this. But if you remember the OpenGL coordinates go positive x and positive y like that, right? And so if we want this as a position, we want to go positive here but negative here, but we are not doing that here. So we have to do this way, right? So we have to do see that. So let's build. No way, my build is running. Let's get cancel here and run. And something got horribly wrong because it was A, B, C, D, and yes, for the D also, for the D also. So A plus we have to do like this. Vector 2 size dot x minus size dot y, and let's just change this here like this, and now it would work, I guess. Yes, so now it's 0 comma 0 is here, and we can do here. And now let's introduce offset, because as you can see, when we draw a rectangle, we are drawing whatever position we are giving, which is 0 comma 0. As you can see, when we are drawing a rectangle, when we push rect, the position is 0 comma 0, the size is 0.5 comma 0.5, right? So this is 0 comma 0, this is 0.5, this is 0.5. And now you are also wondering that why this rectangle is not square, because we are defining our size on x and y the same. Why is it not showing a square? And we'll get it into the next episode next time. Currently what I want to fix is this position thing. So what I actually wanted to draw here was this. Let's change our color. So what I got is this is my position and this is my size, right? So this is my size, like this thing is my size. What I actually want is this. My position should be here, and then this is my size, this is my size. And for that, we can do hard code, we can hard code also. But sometimes we also want position here. Sometimes we want our position to be here. So what we can do the best is define size and offset, right? So now we have position. So now we have position, size, and offset. So offset is basically how much the incoming position should be offsetted to draw in center. So if we pass in 0.5, 0.5, our position would be offsetted 0.5, 0.5, and our position would be here and draw the center. If we define our offset to be 0, 0, our position would be here. If I define our offset 1, 0, my position would shift here, right? And how we do that? So the way we do that is, so let's understand the math here a little bit. So this is like basic linear algebra thingy. So we have a rectangle and we are giving arbitrary position, we have arbitrary size, and we have arbitrary offset. From these three, we need to find these four positions. Right? Basically, that's the problem. If my offset is 0.5 comma 0.5, this position would be here. And now this I have to minus x and plus y, right, to get to this position. So that's I have to do. So from the position, so this is my position, right? To get this point I need to minus, okay, let me just change my size. So this would be like, Yeah, let me just change my size to size.x and minus size.y. And then, so this is my position. So I need to go up. So I need to minus my size, but my size, so if I'm exactly at the center, my position is exactly at the center, then I have to minus size divided by 2, right? So if I offset my point from here to here, I have to subtract this out, which is my size, my width divided by 2, and I have to subtract this height, which is height divided by 2, or I have to add the height, right? I have to add the height and subtract that. But because I don't know where this position can be anywhere from here, my position could be here also, still I should be able to calculate this point perfectly, and that's where this offset comes in, right? So if I'm when I multiply offset by my size would be relative to this particular offset, and then I can minus that, and that that's how we do it. So I do size multiply by offset, and that size, remember, and then everything is the same. Now once I calculate a, I don't need to consider this position. Now I can calculate all 4 of these points relative to a, right? And that would be the same, but this time I don't have to do this, right? And I don't have to do that because I already did that here, right? I inversed my size y and size x, so that I don't have to keep remember, oh, I need to flip my y. I don't need to flip my y now. My game is still running. Let's close it. Let's build. Okay, so there is error because now push rect need to have offset. So for now, let's just pass our offset to be 0, 0. So now it would be the same what used to be. Now if I do this 0.5, whatever I pass into the position would be center of my rectangle. Let me pass this as 1 and this as 0. So now my position would be at this. So basically offset is my pivot, right? I think, oh, I got a good name, right? So offset, let's change this offset to pivot because it's a better name, right? It's a better name. My pivot would be basically in 0 to 1, and now I can basically choose how I want to draw my stuff. Either I want to draw it from the center, draw it from top left, draw it from bottom left, draw it from middle center, left middle center, right middle center, anywhere I want. And this is a very simple basic API to draw our rectangles, which only thing we need to draw in our game. Right? If you need to draw some complex shapes, we can do it later. Right? This is our first game. We are not doing any complicated. We are just making simple Pong game, and later on we'll create something else, some new game where we'll need to do something else. But for very basic simple 2D game, this is all you need. One more thing we need to worry about is that why is it not square? Right? It should be square, but it's not. It's because of the coordinate system which OpenGL provides, right? So OpenGL 2 does coordinates which are based on the screen -1, 0, 1, 1, -1, right? And that's why whatever we pass in, because my screen is rectangle, so whatever I'm drawing would also be stretched according to my window resolution. So if my window was square, it would look a square, but because my window is rectangle, it is looking like rectangle, but the data is square. So that's a problem, and we'll figure that out how to do this using matrix, right? So we'll use orthographic projection to make our data irrelevant of the screen resolution, right? Our data should look like what it is It should not look like how depend on the screen resolution. Our game should look independent from the screen resolution, and that would be our next task, to understand metrics and projections and how we can use how we can do these things inside the shell. So I guess that's it. Good luck, everybody. So I'm gonna check everything I've done. It's nice. Let's add everything. Let's commit. So extracted drawing code into function, simple routines. I like to call it routines, and that's it, right? Yep. Okay.